Right. So in addition to molecules having these chemical bonds, there also exist as three-dimensional objects. So they have shapes. So molecules are 3D objects. So they have shapes. And the shapes of molecules is very important to their properties and their reactivities. So for covalent molecules, predicting the shape of a molecule is actually quite simple. And what we do is we use is VSEPR. That's the model we use. So VSEPR stands for valence, shell, electron, pair, repulsion. Right. So what VSEPR says is that electrons are negatively charged, like charges repel. And so these valence shell electrons repel one another. So for example, if we drew our carbon dioxide structure in two ways, right, which one of these more accurately describes the shapes? And so what we say is that these bonds and lone pairs as well. So we say that these bonds are made of electrons. That electrons repel one another. And since they repel one another, they want to get as far away as possible. Right. So for example, those on the structure on the left, those bonds are as far away as possible while still being bonded to that central carbon. Whereas this one on the left here is that these bonds are too close to one another, right? They can separate further from one another while still being bonded. So these guys are too close. So that does not accurately describe the shape of carbon monoxide, whereas on the left side, that is more accurate of the shape of carbon monoxide. And so your overall shape of your molecule depends how many things are bonded to the central atom. And when we're talking about shape, we're just talking about the atom and the things bonded next to it. So if you have a big molecule, it's made up out of a lot of different shapes. So for example, if we have a central atom attached to two things, and these things can be usually other atoms, but they can be lone pairs. We'll take a look at that in a little bit later. We have what's known as a linear shape. Right? If you think about this carbon monoxide, it's all in a straight line. If we have three things attached to our central atom, we're going to look a little bit different, right? So this is an example of this would be BH3. Right? So our B is our central atom, and then it's attached to 1, 2, 3 things, right? So when it's attached to 3 things, we call this trigonal planar. And it looks like that, right? It looks like a central atom with then 3 things on the side. And you can think about, this is a triangle and it's planar, it's flat. So it describes it pretty accurately. Next up, we're going to go up to 4, call them things. And so that's methane, CH4. And so here you might think it looks like that, flat, and then with a hydrogen on each corner. But remember that these are 3-dimensional images. And so we can use that third dimension, that coming in and out of the board, as a way for the bonds to get further away from one another, and thus be kind of, happier, if you will. And so when we have 4 things, we're actually the shape of a tetrahedral. So I've got an image of a tetrahedral. So what you can see is you can think about these two as being in the plane of the board, and then this one goes into the back of the board, and then this one is jutting outside of the board. So that's how we draw that. Where these dashes, that means that they're going into the back of the board. And these wedges mean that they're coming outside of the board. Right. So since you're in front of the board, that hydrogen with the wedge is closer to you than that hydrogen with a dash. And we'll take a look at the three-dimensional shapes a little bit more in a little bit. So if you're not, kind of processing this, I'll show you a more better visual representation that you can play around with yourself. So a thing, right? So far, they've just been atoms, can be a lone pair. So for example, in SO2, if we think about the shape of the central atom, and really only central atoms have shapes, terminal atoms, we don't consider them as having shapes. So this oxygen is one thing, this oxygen is another thing, and then finally this lone pair is another thing, right? So we have three kind of things here. And when we have three things, we can have two different types of geometry. So first is the electron geometry. And when we're talking about the electron geometry, we're talking about the shape of the molecule while we kind of say that this lone pair counts as part of the shape. And so the shape that then we get is trigonal planar. So that's the same as that BH3, right? When we're talking about electron geometry, our atoms and our lone pairs count the same. Then what we can talk about instead is the molecular geometry. So when we're talking about the molecular geometry, we just ignore the lone pairs, right? They're still there. They affect the shape of the molecule, but we don't describe what the molecule looks like with that lone pair, right? We pretend that that lone pair isn't there when we're describing the shape of it. And so the shape of this, or the molecular shape of SO2 would actually only be bent. That's the name of that shape. So just another example, we have CH4, which has four things and they're all atoms. So this is a tetrahedral in both its electron geometry and its molecular shape. Then we have NH3, which again has four things, but now one of the things is a lone pair. And so its electron geometry is still a tetrahedral, but its molecular geometry is what we call a trigonal pyramidal. And then finally, we have water. So in this case, we have still four things, right? Two hydrogens and then two lone pairs, but only two of the things are atoms. So its electron geometry is still tetrahedral, but now its molecular geometry is what we call bent. And you can look at this all up through what's called a VSEPR table. So it's a good reference to have, but really you want to be familiar with the shapes. So right, in this case, it's the one that I just got from Google, but you can find all kinds of different versions. They all say the same thing in slightly different ways. So the steric number, what they call here is that's our number of things, right? Whether you have two things, three things, four things, five things, six things. And if you only have one thing, we don't call that a shape. So you've got to have at least two other things attached, right? So when you have two things, you're just going to be straight up linear. When you have three things, your electron geometry is going to be trigonal pyramidal, but your molecular geometry is going to depend on how many of those things are lone pairs. So like we said before, if they're all things, then you're trigonal planar. If one of them is a lone pair, then you're bent. Angular is another word you can use, but bent is more common. And then again, when you have four things, if they're all atoms, you're tetrahedral. If one of them is a lone pair, you're trigonal planar. If two of them are lone pairs, then you are bent. You can see then below, we can have more shapes, but we're not going to cover those because those require more than an octet for the central atom. And then you'll cover that in 101. If you would like to see a more visual representation, go ahead, type into Google PHET, P-H-E-T, molecule shapes, and it'll be the first, second, or first one of the first links. It's similar to that game that we played. Let's go ahead and check it out. Right, same same company or site, whatever. And so you can play around with the shapes. So I would suggest playing around with the model first. Let's go ahead and look at that. And then on this bottom left, you can click molecule geometry and electron geometry. And so you see we have one central atom. We have two things attached. We are bent. And then if you go on the right and you click that lone pair button, boom, we can add a lone pair, right? And you can see now our molecular geometry is bent while our electron geometry is trigonal pyramidal. And we can remove that lone pair, replace it with a bond, and now both our shape and our geometry are trigonal planar. And we can play around with that, so we can add one more thing. And now you can see that representation of that tetrahedral, right? You see how it's not a square because we can use that additional third axis, right, going in and out of the board. So you can see on the top and left hydrogen are kind of in the board. That hydrogen in the back is going behind the board, and then this hydrogen in the front is coming out towards you. And then if we remove one of them, one of the bonds, and replace it with a lone pair, then you can see our electron geometry is tetrahedral, but our molecular geometry is pyramidal. And then you can think about, doing the same thing. There's what water would look like, bent. And then, of course, you can play around with the real molecules as well, right? So there's water. Check those boxes so you can see the shapes and whatnot. We won't worry about the bond angles. You'll have to memorize those in Chem 101, or 101. There's CO2. There's our SO2, right? It's got more of that bent shape. And then there's, our BF3 and so on and so forth, right? There's our NH3. So play around with that, with that overall, and get pretty comfortable with the molecular shapes because they are very important to the properties of the molecule.